Welcome to our next lecture in the series on condensed matter theory. In this video I want to have a look at the solutions of the Dirac equation for a freely moving particle without any potential. And we'll do this just to get a feeling of the solutions that one can have for a relativistic particle. We have here the Dirac equation that tells you that the time derivative of the wave function is equal to a sum over the matrices alpha times the spatial derivative plus the rest mass times the wave function. Alpha I are 4x4 matrices that can be conveniently written down in terms of 4 2x2 matrices, where the 2x2 matrices are the Pauli matrices of the off-diagonals for alpha 1, 2 and 3, or the identity matrix on the diagonal for alpha 4. So mc square enters on the diagonal, once with a positive and once a negative sign, whereas the spatial derivative couples the large and the small component with each other. Now when we want to find a solution for a free particle, we can actually think back of the Schrödinger equation, and there free particles are plane waves, plane wave functions e to the I over h bar, and then p dot r minus et. So we can take a trial wave function and see if we find a similar solution that we have non-relativistically in the case of relativistic wave functions. And we have our non-relativistic solution 1 over v e to the I over h bar p dot r minus et. And what we will add is that we now have to multiply this by a vector, and that vector is independent of r and t. u1, u2, u3, u4. And when we wrote down our Schrödinger equation, we set for our exponential, we take e to the I p dot r minus et. And there is of course no reason to pick this phase. We could have equally well picked a minus phase in here. That would of course then slightly change the definition of the Hamiltonian. Here you get an additional minus sign. But what turns out is that relativistically both solutions are important, whereas in the Schrödinger equation you can just choose a phase and work with that. So we have here both a plus and a minus sign as our trial wave functions. So then the question is, what are the four possible vectors up that we find to get solutions? And for that you can just put in this wave function, solve it, then you get, or put it in, take all the derivatives, your exponent will become the same on the left and the right, and therefore drops out, and you get four equations for four unknowns, u1 to u4, and this you can solve. And we'll find four solutions. You solve this as a linear set of four equations. Let's define a bit of shorthand. uz is pc, the momentum in the z direction, divided by e plus mc square, and uxy is px plus I py c divided by e plus mc square. The z direction is different because we quantized our spin in the z direction. So that's just by the form of the Pauli matrices that we have. If you rotate those through, x, y and z will be different. And of course all of them are valid ways to write down your Dirac equation. There's no need to take spin up and down to correspond to the z direction, other than convention. So with this we can write down our first wave function. We have a normalization, square root of E plus mc square divided by 2 times the energy, 1, 0 for the large component, uz, uxy for the small component, and then r e to the I over h bar, p dot r minus et, and the second solution that we find looks very similar. X, y, complex conjugated minus uz, square root 1 over v e to the I over h bar. Minus et. So we now also can understand why we call the first 2 elements in the basis the large component and the last 2 elements in the basis the small component. For non-relativistic energies, E is small compared to mc square, so these 2 are small numbers. We have a large component with spin up or spin down. So this wave function corresponds to the wave function of an electron with spin up, and this wave function corresponds to the wave function of an electron with a spin down. Note that the electron with a spin up is a linear combination of the large component spin up and the small component with spin up and the small component with spin down. So movements do mix the spin up and the spin down components of the basis functions to generate an electron with spin up. These are the particles that we encounter, so those are the things that we call an electron. We do not say when an electron starts to move it becomes a superposition of an electron and a positron. It becomes a superposition of a large and small component of the wave function, and that is the electron. Now, of course, we have 4 solutions. We here have the 2 solutions for the particle. We find now also 2 solutions where the small component is larger than the large component. uz, uxy, 1, 0, times square root 1 over v, e to the, now here we have this minus sign. Minus et, and psi 4, and the same for the spin down. Now this minus sign was exactly the reason why Dirac started to look for a solution that is different from the Klein-Gordon equation. One in principle can absorb this minus sign in E, change the sign of E, and then you have negative energy solutions. The way I wrote down the equations, the energy is always larger than 0. So we here find our 2 negative energy solutions. These are wave functions for the positron, the anti-electron, with either spin up or the positron with spin down. The antiparticles corresponding to the particles of the electron. If you think of these states as negative energy solutions, then we can easily say, well, the Hamiltonian acting on psi 1 or 2 gives me E psi 1 and 2, the Hamiltonian acting on psi 3 or 4 gives me minus E psi 3, 4. And if you say H psi is the energy, then the energy in this case is positive, and the energy in that case is negative. Doing so would give you an energy momentum dispersion for the electrons and would give you an energy momentum dispersion for state 3 and 4. That is negative. And we have an offset with respect to 0 at 0 momentum of mc squared. And the momentum on the horizontal axis. The 0 should be nicely in the middle. Sorry for that. Now Dirac's solution was very much the same as the solution that we have seen in semiconductors or when we discussed the Hall effect in aluminum. Instead of saying that all states are empty, we put our chemical potential in the middle. The states below the chemical potential are completely filled. So these are now completely occupied. And I can make excitations by taking a particle out and putting it there. That gives me an electron-hole pair excitation, a positron-electron excitation. So we can make positrons by removing electrons from the filled band. Now that will cost you energy. So at that point it will be a positive contribution to the energy to make these kind of excitations. And we've also seen that a hole behaves as if its charge is opposite to what you would expect otherwise. And therefore the charge of these states is positive. Now, instead of then referring to these states with negative energy and saying they are fully occupied, we can immediately write things down in a whole language. We say our energy is positive. We get a minus sign not only in front of the energy but also in front of the momenta, such that when we include the interactions with an electromagnetical field, also there the sign will be changed. And these states behave as if they have a positive charge. So here we basically write down the wave functions with a positive energy for the antiparticles of the electrons, with also the opposite charge. So we do find that we have 4 solutions in our Dirac equation. 2 for the electron with spin up and spin down. 2 for the positron with spin up and spin down. All at positive energies. And that is just the possibility to swap between a whole and a particle language that we have used here. Now, all well and nice. The energy to create an electron-positron pair excitation is 2 times the rest mass of the electron. The rest mass of an electron is 1/2 mega electron volt, 500 kilo electron volt. So we talk about an energy scale of 1 mega electron volt before you start to make these kind of excitations. The energy range of interest is 100 Kelvin, 10 millielectron volt. Then the low energy Hamiltonian is set up by the interactions between the electrons, bandwidths, that's electron volts. The binding energies is Rydberg's, so tens of electron volts, which means that at a few hundred electron volts you're really far away, or you start to get far away from the energy scale of interest. And then you still have 3 orders of magnitude before you can make such kind of particle hole excitations. So yes, it's there. You can find it if you do extremely accurate measurements. But the entire positrons is of basically no relevance for all the material science that we describe and do. That's not true for the entire Dirac equation. Also, the electron wave function is modified. And these modifications are there, they are important. One of the perturbations that we will find is spin-orbit coupling, and that is something you know or probably have heard of before because it does a symmetry breaking. There is also a modification of the kinetic energy, and there is a modification of the potential energy. If you want to do quantitative descriptions, even for materials like carbon, diamond, bond distances in diamond, those are important to get to the percent or sub-percent accuracies that you need. But that's all perturbative. It's all very small. The energy scale where the relativistic effects become non-perturbative is really very, very far away from the energy scales where we work. Even if you include all renormalizations, you're still 3 orders of magnitude away, and you're normally many orders of magnitude away, 6 orders of magnitude away before you can make these kind of excitations. So that's something that I want to look at in the next video. What happens if we now take this and go to the non-relativistic limit, which is of interest for the physics that we have in our daily world around us? What is left over? What do we need to include as perturbations on top of the Schrödingerian equation? And those actually will be extremely accurate for the energy scales that we are interested in. Just the first order correction terms. There are 3 of them. For now, thank you very much. Stay healthy. We see each other later.